Okay, we'll start the session now. So good evening everyone. I am Sabyasachi Panda, my PhD scholar in the Department of Metallurgical and Materials Engineering, IIT Madras. Welcome to the second tutorial session for the course of Materials Characterization. I hope all of you have gone through the video lectures which has been given by a professor for this week, for the week 2, which mostly cover lens defects, then different types of microscopy which covers the bright field, dark field, phase contrast and polarized contrast microscopy. And so as we discussed in the last class, as we did in the last class, first we'll go through those concepts together, and then we'll solve some of the problems which will be helpful for solving your assignments which has been given for this week. Okay. So this will be a live interaction session, so you are free to ask any questions if you have any doubts or something. You are free to ask. Only thing is that since I will be I'll be sharing my entire screen, so I'll not be seeing the chat box once I share my entire screen. So in between class you can you can ask me questions. You can unmute yourself and you can ask questions, okay, if you have any doubts, or at the end of the class also I can answer if you have put your doubts in the chat box, okay. So okay, so I hope everyone can see my the slide number 2. Can anyone confirm?
Yes, sir.
Yeah, okay, thank you. So in the last class we left at as a thin lens equation. We are studying lens equation, and the simple lens equation, if any one of you remember, the thin lens equation is 1 by f is equal to 1 by u plus 1 by v, and the f being the focal length, u is the object distance, and v is the image distance from the object from the lens. So since we are going to study about the light microscopy, and the first part of light microscopy is optical microscope, so one of the questions that we encountered in the last session is that there is a term called magnification, right? Magnification is defined as the ratio of image distance to the ratio of image distance to that of the object distance. So, and this is for one lens, but let's say I have n number of lenses, 1 2 3 4, suppose n number of lenses, then the magnification will be the product of all those lenses, m1 m2 m3 and up to mn, right? But now if I follow this rule, then I can get a magnification of very extremely high magnification using several combination of lenses. But I cannot do that. Why I cannot do that? Because though theoretically this is possible, but in practical aspect it is a very difficult thing, or it is you can say that it's technically it's a little bit difficult. Why? Because there are some kind of defects which are associated with the lenses, which are called as aberrations, okay. So due to these aberrations, we are not able to we cannot put 10 or 100 number of optical lenses in our path from object to the image and get a higher magnification image. Though we can get higher magnification image, but for a microscopist or for us to see the features and critical features or any structural features of an image of an object, we need high resolution also. So not only magnification should be high, but also the resolution should also be good enough so that we can distinguish between 2 points in an image. So these aberrations is effectively these aberrations are defects of lenses, okay. So due to these defects of lenses, we are not able to put 100 number of lenses. We cannot put 100 number of lenses and say that our magnification, we are going till 1 million magnification, or we are going till 5 lakh magnification, and you can come and see We can come and see the atoms, or we can come and see some few column of atoms. We cannot say that. So that is the reason we have to study the defects. And what are the defects that are associated with optical lenses? We will see these. And before going into these defects, I will just tell you that these defects are there for lenses, whether it's an optical lens or whether we are switching from optical to electromagnetic lenses. These defects will be present everywhere. You cannot completely some of these defects can be minimized, but some of those defects cannot be completely removed. We can only minimize as much as possible, right? And what do these defects do? They distort the image at every point. Let's say my object is like this, and in my object, if I am putting my lens, so that means this object is made up of infinite points inside this let's say this object, and infinite points are there. So each point, what will happen, if the defects are present, each point will be distorted in some different way. Okay, some different way. One might be perfectly captured as it is, but we are not sure how our image will look like. So our object is like this, but my image will be looking like this. So each point will be distorted, and what will happen? Loss of quality will happen. And why it will happen? Because the loss of resolution will be there. But in some even in the lenses which are full of defects, which are full of aberrations, there will be some point where the aberrations will not be there. Why it will not be there? Because those aberrations, it is not intentionally it will not be there, but unintentionally some of the points will be there associated with a lens, where your object as well as your image will be free of aberration. Those points are called as aplanatic point. Okay, so our job is to make sure that these defects will be as minimum as possible, and they should not affect our image quality, because the moment they start affecting our image quality, your image will be distorted. You will not get clear resolutions. Okay, so for the defects, we'll see there are different types of defects. One defect will be associated with this aberrations, so that is called as chromatic aberration. Another type of defects are called as chromatic aberrations. We'll go through each and every one of these aberrations, like what do they mean, the chromatic aberration and the achromatic aberration. Okay, so first let's go to chromatic aberration. What do you mean by chromatic? So chromatic means, so this means color, something related to color, right? So chromatic aberration means the defects which we are considering that are associated with the lens, they might be coming due to color. Right? So what, for optical microscope, we are considering that our light is white light, right? Sorry. And this white light is made up of, it's if we are considered that this is a visible light, and this is made up of 7 different color. 7 different color, or you can say 7 different wavelength. So the energy formula is equal to hc by lambda. But this lambda, if we consider if I ask you that for a visible light, what should be the lambda, you cannot particularly answer that question, because visible light range is 400 to 750 nanometer, right? So for a particular wavelength, if I ask you, if I tell you what is the wavelength of, let's say, blue light, you will be able to answer. If I ask you what is the wavelength of red light, you will be able to answer. But if I say that what is the wavelength of the white light, you will not be exactly able to answer. That means our white light contains 7 different kinds of wavelength. So that is why when the single lens causes the light to be deviated by an amount depending upon its wavelength, then what will happen? The chromatic aberration will take place. Okay, for why this chromatic aberration will take place? Because for a single lens, different focal length will be appear will be appearing for different wavelength, right? So why this thing will be happening? Because for each and every wavelength, let's say for violet, for indigo, for blue, the energy will be different. So since the energy of each and every ray will be different, so they will also be focused at a different point. So that is why this chromatic aberration will happen. So now looking at this schematics, let's say this is a white light, right? This is our incident white light. Now this is our lens. Okay, so this is our optical lens. So now after, and this is the optic axis. Okay, and now after interacting, after going through this lens, and after the refraction of the white light through these lenses, you will see, since red, we know that red is having higher wavelength, right? So that is why we are using this red light in our vehicles and everywhere, so that we can see that red light from very far distance. So red light is having higher wavelength. Since it is having higher wavelength, what it will do, it will be focused at this point. Okay, and since blue light will be having I'm considering this one red light and this one is blue light. Let's say blue light wavelength is less than the red light wavelength, but its energy is higher, and the blue light will be, since I am considering now all these lights were white light, but after refraction my blue light is focused here, my blue wavelength, and my red wavelength is focused here, right? So that means I should have got only one ray like this, but instead of that, what I am getting two different sets of points. Let's say I put my image plane, I put my detector in this plane, let's say A plane, right? So if I put my detector in A plane, then the image that I will find, the image that I will get, so that will be somewhat in bluish color. Why? Because here the blue wavelength is, at this point the blue wavelength is focused. If I am putting my image plane, my detector in this plane, let's say B plane, I will be getting an image which will be having reddish color. Why? Because at this point my red wavelength is focused. So that is why if I have to put an image, if I have to put a detector on an image plane, then on which plane I will put, so that the combination of this reddish color and this bluish color, I want my image to have as minimum effect from this chromatic aberration. So what I will do, I want to minimize this bluish color as well as this reddish color. If I want to do that, then where I will put, I will not put my detector in A plane, I will not put my detector in B plane. Rather, I will put my detector in a plane where there would be minimum effect of this this reddish color as well as this bluish color. So this I will put. And if instead of one point, now you can see, instead of one point I am getting a disc of I am getting a disc thing. Earlier I was supposed to get, so if you take I am doing it like this here, let's say, okay. So this is my object and this is my image, right? This was the ideal case. I was supposed to get a point, but instead of point I am getting a disc like structure, right? And this disc like structure is known as disc of least confusion, which we talked about in the last class, but we have not explained, I have not explained that. So this is what called as disc of least confusion. Here why we are taking the disc of least confusion? Because here the image will consist the minimum effect from the blue wavelength as well as the red wavelength. So that is why we have to put our detector in disc of least confusion. And this point where the blue wavelength is focus, that point is known as blue focus. And the point where the red wavelength is focused, that point is known as red focus. Okay, so here in chromatic aberration you have to remember three things. One of them is disk of least confusion, where the effect from both the extreme wavelengths are minimized. Okay, instead of point from here, a point like here, we are getting a disc like structure, and that disc is called as disk of least confusion. And one will be blue focus, one of the extreme end of this wavelength will be blue focus, and another wavelength will be another extreme end of this wavelength will be red focus. Okay, so these are called as chromatic aberrations. So white light when it refracted through an optical lens. And how we are going to so that means this lens will cause more problem for us, because every time we cannot put a red light, every time we cannot put a in an simple optical microscope, we cannot use a single color like red, blue. I simply want to look at a few structures. For that, if I have to customize my optical microscope, then the cost will also be higher. So that is why we want to instead of putting the source, instead of generating a monochromatic light, I want to minimize the chromatic aberration by some other method. So what those other method? Combining lenses of different shape. Okay, that means if let's say I am designing a lens like here, these are the white lights. Let's say my red wavelengths are focused here, and my blue as I said, my blue wavelength is focused here. If I can design another lens in such a way that, let's say I'm designing another lens in such a way that for now forget about this term. After getting refracted from this one, it is going on its own path, this red wavelength. But after getting refracted from this lens, it is coming back to this point, right? Similarly, let's say initially my blue wavelength was supposed to be focused here originally, but when I put this thing, then after getting refracted from here, it will also be going into that point. Got it? So this was the original path. It's a original path. If I am giving 1 and 2 without lens number 2. Okay, and this is the modified path with lens number 2. Right? So if I use different shape of lenses, and not only different shape but also refractive indices also, if they are same, because depending on the refractive index, what will happen, the velocity of that light will also vary, right? So due to that, different refractive indices also are needed to minimize the chromatic aberration. And as I said, the simplest method, but yet the expensive method, is elimination of variation of the wavelength, right? So that requires some complex techniques, so that we'll be eliminating the variation in the wavelength. And use of filter or special lamp, if we can put filters, then also we will be converting this white light, which is a polychromatic light, into a monochromatic light. Right? So this is all about the chromatic aberrations. Now let's say we minimize the chromatic aberration. We don't want a white light. We have now generated a monochromatic light, which is having one single lambda, right? But does that mean that now I have generated generated a single wavelength, but does that mean I will not get any kind of distortion in my lenses anymore? No. Why? Because there is another type of aberration is present in the lenses, and that is called as spherical aberration. What does that spherical aberration do, and what is the mechanism for that spherical aberration? The portion of the lens furthest from the axis brings the rays to a focus nearer to the lens. Okay, see the schematics here, then we will be understanding. Let's say this is my object. Okay, this is my object and this is my optical axis, and this is my lens. Now till chromatic aberration, and whenever I have drawn the thin lens equation, what we have assumed, by default we have assumed a perfection in the lens. Perfection in the lens, what do I mean by that? Let's say, let me go back to this here. Let's say I am drawing one thing. Whenever I have drawn like this, I have drawn an object here. You must have seen that all the time what I have done, I have assumed this lens to be perfect. Perfect means whenever I needed some refraction, I have done the refraction from this optic axis and this from this the lens axis, right? There is a little bit correction. So this is the optic axis, not this one. So this is the optic axis, this is the lens axis, sorry. Yeah, so I have drawn if you have written anywhere, just correct that thing. This is the optic axis, that is the lens axis. So now what we have done, I have taken the refraction of this incident ray always from the center of the lens, always from the center of the lens. Why? Because we have assumed that the lenses are perfect, right? So this is the lens axis, okay, and this is the optic axis. But in reality, if you see, in reality, lens will always have some kind of thickness, right? Thickness in the center, thickness in the periphery as well. It will always have some kind of thickness. Let's say this is N1. N1 is air and N2 is some glass. So if you see it closely, then you cannot say that between when the light passes from N1 to N2, that means from air to glass, it will start refracting at the center point. No, it will start refracting at what? At this point. So there is a clear gap you can see between this and this. But that thing we have not taken into account. By default, we have thought that the lenses are perfect and our rays are getting refracted from the middle of the lenses. No, and that is why another aberration will come, that is known as spherical aberration, right? And how that spherical aberration will come? You see, all these are incident beams, okay? And one thing I want to clarify here, that here I have made several colors of this incident beam. It is not that these several colors do not indicate several different type of wavelength. That means this green is not green light and this maroon is not maroon light. They all are monochromatic. I have just mentioned it so that you will in this side you will be able to see where they are focusing. Otherwise this would have been a clustered one. So these all are monochromatic rays. Okay, I have just indicated different color for to see where they are getting focused. Okay, so they all are incident light. Now see, spherical aberration arise because this black one, okay, this black one is getting refracted from farthest from the optical axis. Okay, that means the center portion of the lens. If you consider the center portion of the lens here, then it is getting refracted farthest. So whichever beam is getting refracted farthest from the central portion of the lens, that will be focused nearer. That means if you see here, just follow this one, okay, it is getting refracted. It is getting refracted. After refraction, it has been focused somewhere here. And this is also from this side also same thing, it has been focused somewhere here, right? It is the farthest one, okay, it is the farthest beam, and here it is the nearest to the, from here if you count, then it is the nearest from the central portion of the lens. and this is why the spherical aberration will come. Why? Because the beam which is furthest from the central portion of the lens, then it will be focused nearer. And if you see here, if you can follow this one, just follow this beam. If you can follow this beam, then see where it is focused. It will be focused here. Why? Because it is close to the central portion of the lens, and due to this mechanism it is focused here, right? And similarly, if you put a detector in this plane, then you will be getting the image which consists of only this beam, incident beam. If you put a detector here, then you will be getting image which will give information which will consist this beam, the black beam. So what do you want to do? You want to collect all the information from the object. So if we want to collect all the information from the object, then we have to find a minimum between them, and that minimum will be, instead of so here you see, here it was an object, but here it will be consisting all the beams which are coming from the object. If you want to get a good image, then you want to get all the as maximum beam as possible which are generated from the image from the object. Okay, then only you will get a good image. So to get a good image, what you want to do, you want to calculate, you want to get all the incident beams which are all the refracted beam after refracted from this lens, and this will give you the disk of least confusion. Okay, that means if anyone asks you where the image, where the detector will be there, so on the disk of least confusion, here you can put your detector. Okay, and another thing, the nearest point where the one of the rays is focused, that point is known as marginal focus, and the furthest point, okay, where one of the rays is focused, that is known as axial focus. Okay, so these are the two different kinds of aberration. One is spherical aberration, another one is chromatic aberration. Both aberrations are known as on axis aberration. Why on axis aberration? Because all the aberration that you got, let's say this is your optic axis, this is your optic axis, all the aberrations that you get, it is on the optic axis, it is not deviating outside of the optic axis. You are getting all of your rays are focused on the optic axis, right? So even if this marginal focus is there, it is focused on your optic axis. Even the axial focus is focused at a different point from the disk of least confusion, it is focused on the axis. Same thing for chromatic aberration as well. Okay, so that is why these kind of aberrations are known as on axis aberration, while there are different kinds of aberrations are there which are known as off axis aberration. Okay, off axis aberrations, one of them is astigmatism. What do I mean by off axis aberration? You see, this is the optic axis, this is the optic axis. Instead of the rays being focused here, let's say I deviate my object a little bit from the optic axis, you will see the three-dimensional variation will be there. If you can see, so one of them will be tangential plane, and another one of them, let's say this is my point and this is my lens, and one of them will be tangential plane and another one of them will be sagittal plane. That means one of them is, here it's written, one of them is equatorial, another one is tangential. Okay, so what will happen? Off axis image of a specimen point appearing as a line or ellipse. So if you are putting a point here, it will appear as an ellipse or as a line. Okay, that thing, because what do I mean by this astigmatism off axis point? Let's say you always cannot have a point. We are living in a three-dimensional world. So let's say if you want to put a circle or any kind of three-dimensional, let's say a cylindrical cast iron, you want to see its structural features, then what you will do? That cylindrical iron, the line which passes through the center of that cylindrical iron, only that can be put here. Okay, and let's say I am putting, if I draw like this, okay, let's say my sample is like this. For now, consider my sample is like this. So off axis aberrations means my on axis, let's say it will give correct image on this point, okay, the point which is passing through the center of these things. But all these point where I am putting my dots right now, all these points, they are not on the optic axis. So when they are not on the optic axis, I will get a good image for all the points which are lying on this, from here to here. I'll get all these things. I'll get in the image also, I'll get all the points here. But for all the points those are mentioned here, I will not get a point. What I will get either a line or I will get an ellipse. Okay, so that kind of aberration is known as astigmatism. Okay, so why it happens? Because in 3 dimensions, when we see the tangential and the sagittal plane, they cannot focus at a perfect point, or their focusing ability will diminish as you go from the optic axis. What will happen? The intensity ratio will decrease of the image, and eventually definition, detail, contrast, everything will be lost. So that is known as your one of the off axis aberration, and this is which is known as astigmatism. So to see, I am just going to show you one video how the astigmatism is affecting this thing. See one video here. If you can see, first it was at normal position. So when you take your object to the towards the tangential plane, and you are leaving it here, you can see when it is going to, okay, now it's in normal mode. Okay, we will see another one of the atom. So let's see here, when I am going to the tangential mode, when my object is moving towards the tangential mode, you can see all the radial distance in this way I can see. And when I am going from sagittal mode towards the sagittal plane, this is completely getting blurred, and I am getting some this is clear. And okay, another one, if I am going, you see, when I am moving towards the tangential, the off axis, my object is moving towards tangential, this portion is getting clear. Now when I am going towards sagittal, this portion is getting clear. Okay, that means when I am going tangential, I can see the tangential points clearly, and when I am going sagittal, when I am taking my object towards the sagittal plane, what I am seeing? I am seeing the radial. So when I am seeing the radial points are focused at that time, leaving the tangential point. That means points on this plane and this plane, they are getting blurred. And when I am putting tangential mode, what is happening? The tangential points are focused, leaving radial points are completely blurred. But so see, this is my complete image. I want to get an image like this, right? I want all of my my rays which are coming after refraction from this lens, I want all of them to be getting focused at this. But when I am moving my sample from this optic axis, then what is happening? So this is a complete, currently this is a completely focused image. If you see, so this is a completely focused image. You can see this point, you can see this point, every point you can see. But if you go from the optic axis towards the tangential plane, then what will you see? You will not be able to see from this side. This side features are getting blurred. Similarly, when you are going from optic axis towards the sagittal plane, what will happen? You will see this planes. This side images are very good, but you will lose the quality from this side, right? So this kind of aberrations are known as astigmatism, which we definitely don't want to see, because we want to see a complete focused image, right? So this is known as astigmatism. And similarly to the astigmatism, there is another kind of aberration which is associated with the lens, is called as field curvature. Field curvature is after refraction, what will happen? This is a flat specimen. Okay, so this is a flat specimen. Which one? which you are seeing on the screen now. This is a flat specimen, but after refraction you will see that there is a curvature kind of. The image is giving you a perception that the object is a little bit curved, right? And this surface is known as Pascal surface, and so instead of getting a flat specimen, the image of a flat specimen, you are getting an image of a curved specimen. So that means you will not be able to know whether you're, let's say I am analyzing some unknown samples, right? Some unknown samples, if I put it under the microscope and I see it, and I see this kind of structure, then what I will see, what I will say, that this sample is a little bit curved, then my analysis will be completely wrong, because I do not know the sample. But if but why this analysis has become wrong? Because this lens has this field curvature effect. Okay, so a simple lens focuses image points to of an extended flattened object to a spherical surface resembling a curved ball. It's like a ball where we sometimes we eat something using a bowl, like bowl of water or rice we eat. So it's like that. It's a two-dimensional thing, but in three-dimensional it's like a bowl. Okay, so when this kind of effect takes place from lens, so that is known as field curvature. Okay, it is also another off-axis aberrations. Okay, then come distortion. So distortion means every point in an image, what is happening from depending upon the image from the distance from the axis, what it does, it deviates from its original shape. Okay, how and why this arises? Because different areas of the lens have different focal length and magnification. I told you, if you remember earlier in the second slide, I think in chromatic aberration, that for different wavelength it is the lens might act as different, the lens might have different focal length, and that is why red wavelength is focused somewhere, blue wavelength is focused somewhere. Same thing is happening here also. What? For different areas from different points which are situated at a different distance from the optic axis, they will also have different focal length and magnifications, and since they will have different focal length, the image will be distorted. Okay, and there are two kinds of distortion. One is barrel distortion, another one is pincushion distortion. Okay, what do you mean by barrel distortion? Barrel distortion means the magnification here decreases as you go far from the, let's say this is my optic axis, as you go far from the, in this direction, let's say I am going far from the optic axis, the magnification decreases. Okay, so far from the axis. Okay, this is known as barrel distortion. And the pincushion, you can see that this thing, if you remember the condition for buckling, when we apply some load to a certain material, then there is condition before buckling, there is a condition for barreling. Barreling, it's means like when you are compressing some of the things, with mechanical, when you are loading some things, then what will happen? The top and bottom portion will be in their respective set, while this the radially they will start to grow. Like that means isotropically, you can say they will start to grow. So it's a cylindrical shape. You can imagine the cylindrical shape, they will isotropically start to grow. It's like this one is the original shape, let's say, and I am applying some load here, P. And what will happen? This will be like this, this will be like this, this will be like this. Okay, P test and P test, if I am saying. So this is known as barreling. Okay, same things is happening here. So you can see all these axes are going away from the, like this. So this is known as barreling. So this distortion is known as barrel distortion. Pincushion distortion, what is happened? The reverse happens. The magnification, it increases as you go far from the axis. Okay, so this is known as pincushion distortion and barrel distortion. So there is this is also another off-axis distortion. Another distortion is also known as coma. Why coma occurs? Because non-axial points, they appear as elongated comet. They take the shape of elongated comet. Why that thing happens? Because sin I by sin r does not remain constant in that case. Okay, when this thing does not happen, then this coma things occur. And let's say you are taking a point here, and your elongated comet shape, it might be perpendicular to this optic axis. You will get some kind of some deviated shape kind of thing, means comet like shape you will get. It's like a distortion as well as perpendicular to the optic axis. You will get some weird shape, that is the coma. And how you will correct it? Correct this means sin I by sin r. Okay, sin I by sin r is equal to constant. Why sin I by sin r is important? Because sin I by sin r is equal to let's say I have two medium n1 and n2, then n2 by n1, right? So n2 by n1. So if this is not constant, that means the refractive index is varying. And so if my refractive index is varying, means my velocity is also varying. So if my velocity for different points in my different points in the object, velocity of light coming from the different points of my object are varying, then if their velocity is varying, then their focal length will also be varying. And since their focal length will be varying, they will be giving some weird shape, and that gives to this distortion that is known as coma. Okay. And yeah, another thing that we need to minimize this distortion as minimum as minimum as possible. So I have told earlier that the correction of chromatic aberration, how we can do. Also, one of the important thing in chromatic aberration is how we are choosing our lens, right? So depending on the lens also, we can rectify the chromatic aberration. Why the material which we are choosing for lens is important? Because the refractive index of a transparent isotropic material for a shorter wavelength, okay, is greater than the refractive index. Okay, if I am saying this, okay, let's say refractive index of a shorter wavelength I am considering as ns, and refractive index of longer wavelength I am considering as NL. So for a transparent isotropic material, this thing will happen. Refractive index of an isotropic material for shorter wavelength is greater than the refractive index of NL, right? So that means if I'm light microscope, means if I'm impinging my white light to a lens, then there will be different kinds of wavelength will be there, from red to blue to violet, indigo, every wavelength will be there. But depending on the and since they are having different wavelength, different refractive index will be there. Different refractive index will lead to different velocity. Different velocity will lead to different focal. Their focusing distance and focal length, everything will vary, right? So that is why which material that I choose for design of my lens is also important if we are considering the correction for the chromatic aberrations, right? Generally, what material chooses? One is glass lens we choose, another one is fluoride lens, which is made up of calcium fluoride. Okay, these two materials we choose for our lenses. And there is a term called reciprocal relative dispersion. What do that mean? So reciprocal relative dispersion, how I will know that my whichever, let's say glass lens and fluoride lens, these are the two types of materials. Let's say I want to design some other lenses as well, some other materials which I think that okay, these are also they can be a good lens in future. So how do I know that these materials are good for it can be used for lens applications? Then the number which gives us that whether or not this material can be used, that is called as reciprocal relative dispersion, or this is known as Abbe's number. We all remember Abbe, as he has given the criteria for Aves criteria for image formation, at least in the last class, that is at least two images from the object has to be superimposed and recombined in the image plane so that the image will be formed, right? So same, this reciprocal relative dispersion is the Aves number. Okay, and what does it say? It's a measure of how much a material disperses light. Okay, how much light it is dispersing, that will, let's say this is a glass lens, and if my white light is giving, then how much dispersion it is doing. Okay, so that is this reciprocal relative dispersion or Aves number. If we are saying that Aves number is V, capital V, then this dispersion is this will tell us whether this material will be used for lens or cannot be used for lens. Okay, it is calculated, I think in the lecture it has been denoted as nu, so it is calculated as Nd minus 1 divided by Nc minus Nf. Okay, so this is what the reciprocal relative dispersion tells. This is the significance of reciprocal relative dispersion. As mentioned here, the higher Abbe number, this value generally lies between 25 to 65, I think, and the higher Abbe number indicates less dispersion. That means if we are getting a higher Abbe number, that means our material is good for being used in the lenses. Okay, so this is a measure of how much a material disperses light, right? And this Nd, Nc and Nf, they are the wavelength, the refractive index of a specific wavelength. This Nd is for sodium, and Nc and Nf for the hydrogen. Okay, C line and F line for the hydrogen, right? And then come the eyepieces. So so there are different types of lenses when we are talking about the light microscope. One will be objective lenses, which will take all these lights from the image, from the object, and then it will focus to a image plane. And then how we will see, though the objective lens will focus the incident beams that are coming from the object, then to see, still we need a little bit higher magnification, and that higher magnification we are generally getting by eyepiece lens, or these are sometimes also known as oculars. Okay, and the function of these eyepieces are to magnify and view the image produced by the objective. Simple, just to examine, you can say, to examine and magnify the primary image, so that, and how much it magnifies, 500 to 1000 of the objective we generally require that thing, and that magnification is given by eyepiece. Without, remember, this magnification we achieve without distorting our image quality, because if we are adding one more lens in such a way that it distorts our image quality, then that lens is of no use, right? And also these eyepieces are used sometimes to correct the residual chromatic aberration, though we can say that this chromatic aberration, we have designed our lenses in such a way that the chromatic aberration will be minimized and all, but still always chromatic aberration will be there. In when you go further in electron microscope, still these aberrations will be there, spherical aberration and chromatic aberration. You can still completely remove the spherical aberrations, but you cannot remove the chromatic aberration. You will see there why the chromatic aberration cannot be removed, and I think still involved in only 3 chromatic aberration, completely remove the chromatic aberration. Only 3 microscopes are there in the entire world. So chromatic aberration is a little bit difficult to remove, both in case of optics, light optics, as well as electron optics. Okay, and also another function of this eyepiece is the flattened field of view. Like if the field of view is like this, last class, if you remember, I have told 2 things. One is field of view index, which is S, another one is angle of view, which is sigma, right? So field of view means if you are getting a field of view like this, then you cannot operate, you cannot get image from different places. So the eyepiece job is to make the field of view like this. Okay, so that in one magnification you will be able to get all this information. Okay, you can move your lenses to any of these points and you will get the image, a good quality image. And there are two types of lenses, one is field lens, another one is eye lens. Okay, so details of these field lens and eye lens are not in the scope of this thing. So I'm not going to explain those things, but you have to for your knowledge you have to remember there are two types of eyepieces, one is field lens, another one is eye lens. Okay, so astigmatism also in some cases it is used to correct the flatten the field of view and correct also the astigmatism. So main function of this eyepiece, if anyone asks, you just say that the primary function is to examine, magnify the image which is obtained after the focusing action of the objective lens and to correct the astigmatism and minimize the residual chromatic aberrations, right? And then comes another term which is known as optical path length. Optical path length, I have done one problem related to optical path length last class, if you remember, that is given by n into t. Okay, so what does that optical path means? Optical path means the number of cycles of vibration experienced by a wave between 2 points. Let's say I am considering these points, one is point A, another one is point B, and now I am considering that light is of wave nature. Let's say my wave is going like this. So how many cycle of vibration it has experienced between 2 points? So there will be lots of points like that. Okay, but between 2 points, let's say there are n number of points are there on this sheet, but between 2 points, whichever I am considering, C, D, E, let's say another point F, right? So there are 6 points are there, but between 2 points, what are the number of cycles of vibration experienced by this wave? So that is what will give you the optical path length. Remember, and this optical path length is given by product of refractive index. So I am writing it here. Optical path length is NT. Okay. Another thing, NT is the optical path length, but the number of vibration, if I the number of vibration, right? Here the cycle of vibration experienced by wave is optical path length, which is given by n into t. N is the refractive index, t is the thickness. The number of vibration, when I am considering my wave is of wavelength lambda, then that will be given by nt by lambda. Okay, so this one you have to also remember, the number of vibration is nt by lambda and optical path length is nt. Okay, now if I am seeing, if let's see this image here, so this is an object and this is an image, right? So from object, two types of waves are going. One is, let's say, wave 1, another one is wave 2. Okay, and here if you see, the path of wave 1 and path of wave 2 are completely different, but at the end they are doing a constructive interference and they are forming an image, right? But still, so seeing this image, you can say that wave number 1 and wave number 2, they are here, let's say, consider this lens is of refractive index n and the thickness is t, right? So if I am considering this considering the optical path length of wave 1 and wave 2, what will be the optical path length in the case of wave 1 and in the case of wave 2? Will there be any difference? According to my formula, the optical path length for wave 1 and wave 2, they both will be nt. They will not vary, but you can see here, right? Wave 1 is traveling more distance through this path, wave 2 is traveling through this path. That means less distance. That distance is known as your geometrical distance. Okay, that distance is different, geometrical distance. Geometrical difference distance for wave 1 and wave 2 are different, 1 and 2. This is different, right? So whatever you are seeing visually here, that wave 1 is traveling more distance and wave 2 is going in a straight path on the optical axis, that is different, that is geometrical distance. But the optical path length is how many number of cycle of vibration it has gone. If you see here, the number of vibration here, let's say they are in phase here, right? here also they are in phase, but here if you look at this point, if I am taking, right, if the minima I am considering, their minimas are not coinciding with each other, right? So what is happening here inside this point, for the wave number 2, which is the green one, what is happening here? The number of vibrations, vibrations are more inside this thing, right? And here what is happening, the number of vibrations are less, right? It is, so here if you say 1 2, that's all. Here 1 2 3, right? So that is why even if this one travels, the wave number 1 travels more geometrical distance, okay, the velocity of wave 1 will be higher as compared to the velocity of wave 2, right? Why? Because inside the material, inside the glass lens, it will, the inside the glass lens, since the thickness is less, it will be moving faster and it will be going outside easily. But here it has to, the velocity will be decreased a little bit, and that is why it will go a little bit slowly. And by the time, though it is covering less amount of geometrical distance, the optical path length traversed by beam 1 as well as beam 2, they both are same, okay. And if the formula for number of vibration, here I have told nt by lambda. If the overall optical path length, which that means the number of vibration of when you are considering air and in glass, both you are taking consideration into, then that it is just a summation, nothing more. Number of vibration is n1 t1 by lambda 1 and 2 t2 by lambda 2, okay. So this is the optical path length. Here one thing you have to remember, the geometrical distance and optical path length, they are completely different thing. Though the geometrical distance is different, for 1 and 2, the optical path length is same. Okay, now coming to the light microscope, because we are studying optics now, the light microscope. So what do we see in the light microscope? We see generally some surface features of a material or structural features of a material, and we see whether the material has any kind of shrinkage, whether any gas porosity is there, cracks are there, inclusions are there. So these are different kinds of features that we see generally in light microscope. And to see the feature, if you go and put your sample just like that, if you prepare any sample, put under light microscope, you will not be able to see many features. Why? Because the microscope will, and to see it in a light microscope, you first have to mount the sample, then you have to grind the sample, polish the sample, and then there is even if after polishing you will be able to see some of the features. But if you want to see all of these features, then what do you have to do? There is a process called etching, right? Etching is a controlled corrosion process. That means it's an electrolytic. What will happen when you do an etching on your sample? An electrolytic reaction will take place on different surfaces depending upon its potentials, okay. So that when that thing happens, all means your different surfaces will reveal themselves to outside, and then if you put your sample under the microscope, you will be able to see those things. And etching are done by, generally two types of etching are there. One is thermal etching, another one is chemical etching. So thermal etching means you take a sample. It is generally done for ceramic samples, because ceramic samples are very difficult to etch chemically. So thermal etching means you etch it using heat. Heat means temperature, okay. So how it is done? Let's say for ceramics there is a temperature called sintering temperature, right? So sintering temperature is there. So sintering temperature minus 150 to 200 degrees Celsius. So temperature less than, okay, temperature less than 150 to 200 degree Celsius, less than sintering temperature of the ceramics. You put the sample, you heat the sample till that temperature, and then take it out. Then you will see the grain structure and all these cracks inclusion, okay. That is known as thermal etching. For metals we do the chemical etching, because if we take the metal to higher temperature, then the different reaction might also and the elastic plastic transition will happen, and it might lose its properties. Slow heating, if you do, that will be a problem. So we do the chemical etching. So there are different chemical reagents will be there. You have to find out which reagent is used for which kind of metal. So these chemical reagents will be there, and when you do the chemical etching and the crystal faceting and selective phase dissolution, so these are different kinds of mechanism which act in a chemical etching. And due to that, let's say your material is like that, and your grains are something like this, and all these grains, and inside grains, all this, let's say some porosity is there, some crack is there. So all these things you will be able to see. Until and unless you do the etching, you will not be able to get a good microscopic images. So it is always recommended to go for etching before you put any of your sample under microscope. Okay, what does this etching do? Reveal the size of the grains, phase morphology, compositional gradients, and other orientation related edge bits, right? So one is temperature, another one is chemical agent, right? So this is what known as light microscope. So now we'll see the methods of microscopy. That means what are the different modes of what are the different modes that we can use our microscope. One is bright field microscope, another one is dark field mode of microscope. Then we can use the microscope in polarization contrast mode, phase contrast mode, interference contrast mode. I think we have in this week we have covered these four, not this one. We have not covered this one, but bright field, dark field, polarization, and phase contrast we'll just see it in brief. So in the bright field, these are the methods of microscope, and these are the methods of illumination that we can do by keeping our object. So one is amplitude object in bright field mode. So I'll tell you what is the amplitude object. So just for now, you just remember this term, amplitude object in bright field mode. Then another term comes phase object. So amplitude object and phase object, they both are used in phase contrast microscopy. Okay, and birefringent substances, this thing. So this thing, I'll just write it down. These objects are used as phase contrast microscopy, and birefringent, this is used in polarized microscopy. Okay, and structural changes in the object based on the refractive index also we do sometimes the we take into consideration that factor also while we are illuminating the sample. Okay, then comes bright field. So the bright field, as I said here, one of the methods of microscope. So bright field microscope, that means the direct light reaches the objective. Microscopic image, so here in bright field means direct light reaches the objective. Microscopic image is formed by diffraction plus refraction plus absorption of light, right? Always people get confused between bright field and dark field image, like which one in bright field, which one is bright, whether the background is dark or the background is bright, whether the image is bright or the image is dark. And in same case also happens in dark field, that whether the image is dark or the background is dark, or which one is dark, they always get confused. So here you do not have to get confused, rather you just understand the simple mechanism. So here in bright field, what happens, let's say my sample is this one, my light is this. This is my light, and okay, this is my specimen stage. This is my light source. Okay, and here I have kept my objective, and here I have kept my screen or detector, you can say. Okay, so bright field means, let's say my rays will be going like this, and also some rays will be going like this. So after refraction with this is my sample. Okay, this is specimen stage, this is my sample. Okay, and this is my light source. This is not my object, this is my object. Okay, this is the sample. So after refraction from the sample. For now, let's say I am considering my sample to be a little bit transparent. Okay, so after refraction, my some of my rays will be going in this direction. I will tell them as, for now I will tell them as diffracted rays. Okay, instead of refraction I am referring them as diffracted ray. So now if you see here in this picture, if you see, this is a very the simplest schematics I am drawing for you to understand the bright field microscopy. So let's say this is my objective, and through which the this things are going, the diffracted rays are going. Okay, so this one. Okay, so you see the rays which are interacting. This is my light source. So from my light source some rays are coming and they are interacting with my object, and after interaction some will be diffracted, some will be non-diffracted, or I will call them deviated, non-deviated, sorry, non-deviated, right? That means they are straight, they can go as it is. So after interaction of this beam of this light with my sample, let's say like this, after interaction of my of the beam with my sample, some rays will be diffracted, some rays will not be diffracted, right? So the diffracted okay, let's say my objective is like this. I'm keeping a objective a little bit bigger so that you'll understand. Okay, so after diffraction, some rays which have gone through like this, they will directly be passing through without interacting with my specimen. Okay, those rays I will call them non-diffracted rays, and some rays they will interact with my specimen and they will be going in a particular directions. Okay, so all the rays which are not getting diffracted, they will straight hit the screen here. They will straight hit the screen. This concept I hope you are able to understand. All the rays which are not interacting with my specimen, but they are captured by your objective. Okay, they will all go and hit the screen, and since they are not since they are directly going and hitting the screen, so all these rays will create a bright illumination on your screen, right? All these rays which are undeviated, they will create a bright illumination on your screen, right? And all the diffracted rays, right, which are going and hitting and interacting with your sample, though they are also captured by the objective, but they will not be able to give that much illumination which are the non-diffracted rays are giving. Okay, so that is why on your screen, let's say on your screen, the illumination, the non-diffracted rays are giving more intense illumination.
Excuse me?
Yes.
Sorry, sir. Movement, your pointer not visible to me.
Which pointer?
This you are showing that the objective lens and you are drawing it. So how when you are moving it, showing that how it is moving on that along the rays, all things, not able to visible it. Can you make your
Is
pointer a little bit bigger in size?
sorry?
Like mouse, na? You have the pointer, correct?
Yeah, I'm writing. I'm using the pen currently.
Okay, you are using the pen current because when you are showing it, it is not visible
No,
to
no.
all.
I'm just using the pen. That's all.
Okay, okay,
Yeah.
okay. It's okay, it's okay.
Yeah. So pen is moving, right?
Not we cannot see that. That is the
Okay,
reason what you are
the
telling. Suddenly, I think that is some disconnection to understand is there.
Oh, okay, okay. Yeah,
Sorry.
no problem. Yeah, I'll write it on the PPT itself. No problem. So everyone can see, right? Whatever I'm writing currently.
thing is visible.
Yes, sir. Yes, sir.
You're moving it, your pointer, this pen dot, like you are saying, this is the objective. You're like if you have the mouse, you can show the arrow. Correct?
Okay, so I'll
Yes, sir. That pen pointer is very small. I
Yeah.
think that is not required. I think.
which no, I'm currently using the pen, so that is why you will not be able to see the pen. But whatever I'm writing on the PPT, the slide, you will be able to see it. I'll try to write
Okay.
everything on the slide. So yeah,
Okay.
thanks for pointing out.
Thank you. Thank you.
Yeah. So yeah. So as I said, these points, all these points, let's say these points, they are illuminated by the non-diffracted rays. That means their intensity is much more higher, and the, let's say, all these rays which are coming after diffraction from this after diffraction from the interaction between, let's say, my object and the beam, so their intensity will be a little bit like, let's say, if I'm saying this is one region, this is two region, this is three region, the intensity will be too much high for region 1 and region 2, okay, and intensity will be a little bit less for region 3, right? So this is the region. In a bright field, the background which I am considering this is always bright, because the background will be consisted of the non-diffracted ray, and my sample which I am seeing, that will be always dark. This is the simple schematics and the simple mechanism for bright field microscopy. So in bright field microscopy, always the bright refers to the background. So in bright field and dark field, you always remember the background, it refers to the background. Bright means the background is bright, and dark field means the background is dark, okay? So same thing, if we reverse the situation now, in case of dark field, then what will happen? In bright field, the direct light were reaching the objective. Here the direct light were not reaching the objective. We'll see how the direct light will not be reaching the objective. And the image formation, if you remember, in bright field the image formation was due to diffracted light, due to non-diffracted light, due to absorption of light, everything. But here only the diffracted light will contribute to the image formation. And dark field means background is dark, okay? Dark means background is dark, and due to that, what we will be able to see, the edges, the cracks, whichever is present, whichever are present in the sample, they will be appearing bright, okay? So in bright field microscope, if you want to see an edge or a crack, you will not be able to see. If you want to see all those things, then you have to switch to dark field mode, okay? And due to that, smaller particles, any minute phase objects which generally we are not able to see in bright field, we can always detect them in dark field mode. And these are the different kinds of diatoms, bacteria, isolated organs, and all these things, small living cells and tissues, will be able to see it. So that is what dark field means. The let's say entire background is dark, this is dark background, this is white object. So bright field means bright background, dark object, dark field means dark background, white object. Now don't see this one because I have written them for your understanding. Just look at this picture, what I was saying. See here, what is the dark field? How I can say that, how we are not able to we will place our objective in such a way that the objective will not collect the non-deviated ray, it will collect the diffracted ray. That is a little bit it is a little bit tricky, right? So how we will do that? Because we if in general perception, let's say we are keeping our lens like this, and any lens like this, and this is this is our sample, and beams are coming like this, okay? Incident beam, this is our sample, and the rays, these are the non-deviated rays, right? And these are the diffracted rays. This is how we have perceived our sample currently, right? So these are the diffracted rays, and these are the non-diffracted rays. So since non-diffracted rays we are getting, and this is the lens. So now in this combination we are able to see, we are able to visualize currently that this is non-deviated, this is diffracted. Then how to put our specimen, or how to put this lens in such a way that we, now I have told that dark field image will be consisting of the diffracted ray. So so if I am considering this as my lens, shall I change the position of my lens from vertical? Shall I change my lens to this, like this? Shall I do that? This is the question. So this is, let's consider lens. So shall I do that from here, shall I do that? No. The answer is, if I can do that, but the problem is it will be more complicated system. Rather than doing so there is another possibility. Let's say what I will do, this is my sample, right? This is my sample. So my sample is currently like this. Shall I change the orientation of my sample like this or like this, so that my incident beams will come like this, right? So shall I do that? I can do that, but that will also create another problem. I cannot keep any more, I have to then hold my sample tightly to the specimen stage, otherwise the sample might fall down, right? So that also creates another problem. So what I will do, I will not change the lens, I will not change the lens position, I will not even change the sample stage also. What I will do, I will change the illumination system. Okay, how I will change the illumination system? Now see, here this is the illumination from the source, this is going, okay, right? Here what I have done, dark field annulus I have put. Annulus means it will stop all the light, all the direct light. I am only now allowing the light on going in this direction, or in a ring like structure. This is a side view, this is a top view of that annulus. In a ring like structure, I am stopping all the central beam from by this one, by this annulus. So I am only allowing through this white light, through these white spaces that are there in the annulus, I am allowing the beam to go there. It will go, and this, what will happen here, there are two different kinds of surfaces. There are different kinds of surfaces I have provided here. Instead of going to the sample in a, let's say, in a flat directions like this, what I am doing, I am reflecting these beams now by providing some kind of surface. Okay, so that is dark field condenser, and this setup is known as dark field condenser setup. Okay, instead of hitting the sample like this, the beams, what I am doing now, I am hitting the samples like this in an inclined angle. Now you see my incident beams are, initial incident beams are going like this. The condenser, with the condenser, dark field condenser, what did I do? I changed the direction of my incident beam from here. Now I change the direction of my incident beam. Again there is another condenser diaphragm I have kept, and that also focus them into a single point onto a, so this is my sample. Okay, in a single point of my sample I am focused. Now you see, instead of getting my sample was instead of impinging my incident beam on my sample at a perpendicular angle, now I am creating some kind of angle. Okay, now that I have created some kind of angle for this incident ray, let's say I am saying for incident ray 1, where I have, so that means this incident ray, for this incident ray, this is the undeviated beam. Okay, and all the other beams which are coming like this, they all are diffracted beam. Same thing, if I consider this side, this is 2, second incident ray. For second incident ray, this is the undeviated ray, undeviated or non-diffracted. Okay, this is the undifracted. But any other beam which are coming like this, they all will be the diffracted beam. Now if I can capture all this diffracted beam like I have shown in a pink color, this area, if I can capture all the diffracted beam, then I will be getting the image which will be made up of dark field image. Okay, so that is the mechanism. This is the mechanism for dark field and bright field image. In bright field we catch these beams, in dark field we catch these beams, the diffracted beam. What will happen? The diffracted beam, I will be able to see, since the interaction between the specimen and my material, specimen and my incident beam will be very less. So that means the amount of diffracted beams I will get is a very low amount. So that is why the cracks and the edges which are present in my sample in a very minute phase, they will be visible in dark field microscopy, because I will be getting those small amount of diffracted beams which I will not have otherwise I would have got in bright field microscopy. And so this is the mechanism for dark field microscopy. And here I have written two ways of creating dark field image. So yeah, I'll share this PPT. If you want, you can read. So these are the two different ways of dark field image. The important thing here is I have highlighted that the numerical aperture of the objective should be lower than the illuminating system, numerical aperture of the illuminating system. And also this is one way of creating a dark field image. These are all experimental parameters. Means when you go to the so these are the experimental parameters. Okay, if you want to use a dark field image. And this is also, so this is the numerical aperture, and also to use a phase contrast annulus that is intentionally oversized than the objective. Okay, so the phase contrast annulus, what is that, we'll see it in the next few slides. So these are the two different ways of creating a dark field images. Okay, but this is the mechanism I want you to remember, that how the diffracted beam we are getting the diffracted beam by not changing the sample stage position, by not changing the objective lens position, but by changing the position of the illuminating system, like how the incident beam is going to fall on the sample, whether it is going to fall on the sample in a perpendicular mode or in some angle mode. Okay, the steeper the angle will be, the more diffracted beam you will get, and that gives us the higher magnification. If we want to use the dark field mode, dark field microscope, we want to use microscope in a dark field mode, then for higher magnification work we need to use the oil immersed instead of air. We need to use the oil immersed dark field condenser, and what that will do, that will give us access to large number of diffracted beam. So the large number of diffracted beam means you can go to a little bit higher magnification as compared to the previous one. And there are two types of dark field for high magnification work. There are two types of these condensers are there, like here these are the condenser, this is the dark field condenser. So for higher magnification work, two types of condenser are there. One is paraboloid condenser, another one is cardioid condenser. So in paraboloid condenser, what happens, the incident beam goes like here there is a parabolic surfaces will be there, and from this parabolic surface they will be directed towards the specimen. Here this is the specimen. And the cardioid condenser, what does it do, instead of doing a parabolic sun, here you can see a spherical surface is there. Okay, so when the incident beam goes like this, so this will be hitting the spherical surface, then it will again change its direction, then it will be focused towards the sample, and this is the sample, and here you will get. So these are all the, whichever I am taking currently, these are all the non-diffracted, non-deviated way, that means direct beam, and these all are the diffracted. So this much, the more diffracted beam I will get, the more information about the object I will be able to extract. So that is why this oil immersed dark field condenser are used. Okay, so this is one of the difference in bright field and dark field imaging in reflected light microscope. Here you can see in bright field imaging, the beam is coming, it is getting it is going like this, and then it is again going, and then the objective is collecting all the rays which are undeviated, right, which are undeviated rays, objective is collecting, and that will give us the bright field. Here you can see the background is white, the numbers are dark, right. So this is a bright field image. Similarly, in a dark field image, I am blocking I am trying to block as much as central illumination, so that is why I have put a stopper here. Okay, so light source will be only going through this, and then it will be angling to this one, right, and then it will go to collect that one, go to this beam, and then finally the background is dark and the image, this 1.8 is bright. Okay, so this is a comparison between bright field and dark field imaging, where remember, any time you remember bright field and dark field, it always refers to the background, not the image. Bright field means bright background, dark field means dark background. Okay, and then comes phase contrast microscopy. So what do we mean by phase contrast microscopy? Before that, there are a few terminology which we have to go through. So one is amplitude objects, another one is phase object. So amplitude object is the difference in the image. These amplitude objects, when you keep these amplitude objects in the path of any of the wave, what will happen? The amplitude difference will be there first of all, and due to amplitude, since we know that intensity is directly proportional to amplitude square, so if there is amplitude difference will be there, similarly the intensity difference will be there. And if intensity difference will be there, last class I have told that the contrast is given by delta I by IB. Okay, so if intensity difference will be there, then contrast will be there, and if the contrast is greater than 20%, then we will be able to 20% or 5 to 20%. If the contrast is minimum 5 to 20%, then we will be able to see the differences between different structural features of our material. So that is known as amplitude object. Phase object is what they do. They just they do not change the amplitude, they just change the phase. Okay, like they absorb some they diffract light, and they how they change the phase. The phase is associated with the path difference, right? The path difference, when we do some kind of path difference, and that path difference and phase difference, that formula is given as path the phase difference, if I am talking about 2 pi delta by lambda, right? So this is the phase change formula, and this is the path difference, and this is the phase difference. So if we are putting an object in the path of any wave, then that object, if it changes the path of that wave, then phase change will be there, and those objects are known as phase objects. Okay, and phase contrast microscope, what does it do? It converts the phase change to the amplitude change, right? It is by some mechanism, it converts the phase change of a material, phase change of the beam, of the incident beam which are getting refracted, the phase change, it converts to amplitude change. Since phase change is getting converted to amplitude change, once amplitude changes, intensity will change. Once intensity will change, contrast will change, and once contrast changes, then we will be able to see. And to see what are the amplitude object and phase object, see here, this is a reference wave, right? And amplitude means this amplitude, let's say this is my amplitude, and after if I am keeping so this is the amplitude object. Okay, so if I am keeping an amplitude object here, you will see the reduction in the amplitude from here to here, right? And this is the reduced amplitude, and due to reduced amplitude, you will get reduced intensity, and then from there you will get reduced contrast, or depending upon the intensity, you will get higher or lower contrast. Okay, but the phase object, since this is the phase object, okay, this is the phase object, what does it do? It does not change the intensity at all. If I am talking about intensity, it has not changed the intensity, but it has changed its phase. How do I know that it has changed its phase? If you see, this is the reference wave, this is the maxima, but now the maxima lies, after interacting with the phase object, the maxima lies somewhere at a certain distance. Okay, so this is known as your phase object and amplitude object. And here, if you can see how the phase is changed without changing the amplitude, this is an example. Here incident transmitted light is there, and if you are keeping a specimen here, okay, and then if you see, it is getting now this point and this point, they are not now similar, they are not in a single line. Okay, so disturbance by a phase object in planar wavefront, you can see the amplitude remains same, but still a pure phase object will change the phase of this thing. Okay, so these are known as phase and amplitude object. Now let's say how in a bright field microscopy, how this phase change happen. Now look at this picture only. So let's say this is or let's consider two types of waves first. One will be the S wave. sorry, one will be, yeah, S wave, another one will be D wave. This S wave is the surrounding wave, it is called as surrounding wave or the non-deviated wave, and this D wave is called as diffracted wave, that's why it is D wave. Okay, so now what will happen, this D wave, the amount of D wave will be very because the amount of diffraction that takes place here is very less in bright field microscopy, so that is why this amount of D wave, this amplitude of the D wave will be very much low as compared to the amplitude of S wave. Now there will be another wave which will be, when we are collecting, when we are going to the image plane, the interference happens, right? The interference need to be constructive, and that is how we will get the image. So there will be another wave which is known as particle wave, P wave. So that is particle wave, and this wave is given by S plus D. Some will be deviated, some will be non-deviated, or the surrounding wave, right? And now see, since the amount of diffraction which has taken place, so when we are keeping a phase object in the path of our wave, let's say I am keeping a phase object and this wave is traveling and I am keeping a phase object. Let's consider this scenario. Okay, if I am seeing this thing in a bright field microscopy, what will happen, since this amount will be very less, right? So this, whatever the amplitude of this what amplitude as well as the wavelength, those things, what will happen, this particle wave and this S wave, they, if I try to what is the path difference and eventually what is the phase difference, if I see, then the path difference will not be more than lambda by 20. Okay, that's what it has been observed in a bright field microscopy. And since the path difference is not, it's close to lambda by 20, so you can see that this P wave, which is the green wave here I am talking, and the S wave, so this is S, this is P, so P wave almost follows the similar trajectory and similar, it has similar amplitude as the S wave. That means the resultant image that I am getting, it is similar to the undeviated ray, right? On the image which has been formed in my screen in bright field microscopy when I have kept a phase object. Okay, then what from all these things, what I have learned, that the path difference is not that much great, and if the path difference is not great, then eventually the phase difference will also be not great, and if the phase difference is not great, then my interference or intensity, not intensity, my amplitude difference will not be that great, and amplitude difference will give to intensity difference will not be that great. That will means eventually my contrast will also be not that great, and if my contrast is not great, so I will not get all the information from a bright field microscopy if I have to see some of the features, right? In phase contrast microscopy, I cannot use, if I am keeping a phase object, okay, then I will not get enough information from a bright field microscopy, right? And same thing, whichever I have told you in an XY coordinate, like in Y amplitude, X being the phase, same thing it has been given in a polar coordinate. Okay, and then that is why I need to design something else. Okay, I cannot simply put the light on my specimen and try to see what are the things that I can see it in the image plane. Why? Because in that way I will not be able to get much difference from my deviated ray and from my undeviated ray and from my resultant ray, because there will not be enough phase difference and there will not be enough contrast difference. Then how will I see what are the features are there in my image, in my object? Then what do? We do some things called, we put some things called phase plate and condenser annulus in our design, right? Those two things, what do they do? Isolate the surround and diffracted rays. Surround ray means S and diffracted ray means D. Okay, and from the specimen they occupy different location in diffraction plane of the objective. So what does it mean? That means this ray, if I am putting some kind of, so this is the condenser annulus which will focus it on the specimen here, and then from the specimen the objective is there, and after objective I am putting one thing called phase plate. What does this phase plate do? This phase plate, what it the thickness of this phase plate I will choose in such a way that the diffracted ray will be, now the diffracted ray will be it will be retarded, the phase of this diffracted ray will be retarded by lambda by 4, and the phase of this undeviated ray or the surrounding wave, that will be advanced by lambda by 4. So now if I am seeing, if one is getting diffracted, one is going undetected here through this phase plate, right? So this one is, this phase plate is shown in here, one will be plus lambda by 4, another one will be minus lambda by 4. If I combine these two, let's say at a certain point in my screen, then I will get a path difference of lambda by 2, which is quite large, right? So even if I get a path difference of lambda by 2, and eventually lambda by 2 path difference means I will get a destructive interference, but still I will be able to see the contrast. That means path, this huge path difference will give to phase difference will give to amplitude difference will give to intensity, and eventually I will get a contrast, big contrast. One will be, so this will be the destructive interference, and somewhere I will be getting constructive interference, right? So that is why, that is the role of this phase plate, and this phase plate we use, since we use, and this kind of microscopy is known as phase contrast microscope. Okay, so what does this phase plate do? This phase plate eventually advance the undeviated rays path by lambda by 4, retard the deviated or the diffracted rays path by lambda. So this is advance, this is retard. Retard means you can say decrease. This is acceleration, this is deceleration. Okay, so retard this path of the diffracted ray, so that we will get different kinds of different contrast in our image. Then that is how we will be able to see some of the features, some of the living cells in a phase contrast microscope mode. Okay, and if we want to see the positive contrast and the negative contrast, same thing. The positive contrast here, if you look, these are the bright and these are the dark thing, and there are two types of contrast are there, positive and negative. Positive contrast, whichever I have explained it here, this is the positive contrast. So instead of passing the undeviated ray through this region, if you block this region and let the undeviated ray pass through this region, right? So that is what will give you the negative phase contrast. Okay, so this is the positive phase contrast, and if you block this area and pass the let the undeviated ray go through this one, and let the diffracted ray go through this one, okay, that will, what that will do, that will also reverse the situation, and that will give you the negative phase contrast. So this is what positive and negative phase contrast. Okay, and in negative phase contrast, if you see this image, these are looking a little bit brighter as compared to the background. Okay, that is how you see the difference between positive and negative phase contrast. Okay, then comes polarization microscopy. So what do you mean by polarization microscopy? So we need the polarization microscopy for the specimen which are having optical anisotropy. What do we mean by optical anisotropy? That means the light interaction, when light interacts with them, there will be some ordered molecules in the material, and they will also be direction sensitive. Since they will be direction sensitive, they will allow light through them in a particular direction. Okay, and they will allow light which are having a particular property, right? And that is bright against dark background. Polarization microscopy, remember, it is a dark background microscopy. That means it is similar to dark field microscopy, but not exactly dark field microscopy, because in dark field microscopy we are not using polarized light. So what do I mean by polarized, non-polarized? Let's say I have some light, this is my incident light, and the E vectors of this incident light are randomly oriented. Okay, instead of this one is a randomly polarized light. And if I want to use my light in a linearly polarized manner, then from this one, what do I will do? This one, my E vector is either in going in this direction or in this direction. So this is a linearly polarized light. How I will get the linearly polarized light and from the random light, I will show it in the next slide. But for now, this is the randomly polarized light and this is the linearly polarized light. And this is a quantitative measurement. Why we do this polarization microscopy? Because to check optical path length. Okay, we have calculated the optical path length previously. To check the optical path length, from the optical path length, if we know the thickness, then we can also calculate the refractive index of the medium. If we do not know, every time we need not to know all the parameters, but sometimes if we have to calculate to something, we can use polarization microscopy. And from the specimens that we can use this polarization microscopy is are mentioned here. Some you can see DNA as well as acetylene filament and spindle fibers, helical strands of cellulose fibers. So all the biological samples mostly they are captured by this polarization microscopy. So how do we get from randomly polarized light to a linearly polarized light? We use a filter. So now in this light, the E vector is randomly polarized. So all direction the E vectors are there. But only after putting a filter, only the polarized light whose E vector are in this direction, they will only be crossed. So from the E vector coming earlier in the last class, I have told that light is an electromagnetic radiation where electric vector as well as magnetic vectors are there. So that E vectors I am talking about. So if I am using a filter, then polarized transmit light, I will get it like that. So now if I put a polarized light here and I am putting, so how will I block the lights? So in this case, after I get the linearly polarized light, if I am putting another filter whose axis is parallel to this one, then I will get the image here in this screen. Let's say I am keeping my screen here, but here if you see, even after getting a linearly polarized light, I am changing the direction again, then all these things will be blocked and I will not be getting, so all these things will be blocked and my light will not come to my screen. Okay, so this is a Polaroid sheet. This sheet is called as Polaroid sheet, or sometimes I think these are called as polars. Okay, so these are called as polars as well. Okay, and then we will see another theory which is known as double refraction of the crystal. So why double refraction? So there are some crystal, quartz, calcite, rutile, tourmaline, and they are optically anisotropic. That means they only allow the refraction to be happen in a particular direction or according to their axis. So that is what optically anisotropic means. They allow the refraction to happen in a particular direction according to their optic axis, right? So why does it happen? If you take an example of calcite, you'll see that there are two. So one is this one, another one is this one. Two calcite you can read. Even you change the even if you rotate it, then also you will be able to see the same thing. Calcite, you can see it here top, and this one is bottom, right? That means 2 times the refraction is happening. And why it is happening? The atoms in the crystals are ordered in a precise geometric arrangement. Then the direction dependent difference in the refraction index happening, and that is why the optical path length will also vary. And due to the optical path length since the optical path length will be varying, so that is why you are getting 2 types of refraction, and this is called as double refraction. I think yeah, so double refraction, it is sometime also here it is mentioned, it is called as birefringence. Okay, so how does this concept of double refraction happen? If you see here, so there are 3 scenarios I have mentioned it here. Let's say one is A, one is B, and another one is C. If we take all these 3, then here this is the incident light. So what happens, this in double refraction, the rays which are the incident rays, they are generally split into 2. Double refraction, why this double refraction takes place? Because the incident ray here is split into two types of ray. One is ordinary ray, another one is extraordinary ray. So extraordinary ray is E, ordinary ray is noted as O. Okay, so that is why ordinary ray is the ray which follows the normal refraction path, but the extraordinary ray is the ray which does not follow the normal diffraction path, rather it starts rotating its E vector in a perpendicular direction to that of the ordinary ray. So here if you see the incident with these three-dimensional crystals, if you see here on the top side of the image, so here the incident beam is coming, it is coming. Now after refraction you will see that this is the E vector of the ordinary ray and this are the E vector of the extraordinary ray. So this I am telling you E vector. So the red are the ordinary ray, this one, and the E are the extraordinary vector. You see this extraordinary vector are they are perpendicular to the E vector. So that is why when you are putting a screen, let's say here on top of your sample, after the interaction of the incident beam to that of the crystal, then you will be getting two different kinds of ray, and due to that two different kinds of ray, the double refraction happens. You will be getting an image of made up of two different rays, and due to that is why it is called as double refraction. Okay, though we generally say that double refraction and birefringence are both same thing, but technically they are not same, because double refraction refers to the splitting of the ray into two resultant ray. One is O, one is E. And the birefringence refers to the cause of splitting. That means the direction dependent variation. Since here you see the direction dependent variation in the refractive index. Okay, so double refraction says that okay, our incident ray is getting split into two types. Birefringence tells us that why it is getting split into two types. Here you see you will get two different double refraction here. Okay, in this case if you consider case number B, then here also, since the optic axis here, okay, it is perpendicular to the incident ray axis, okay, the axis of the crystal. Okay, so this is the axis of the crystal here. If you can see it here, this is perpendicular to the incident ray, and what will happen? It is the E ray and O ray, that means the extraordinary ray and the ordinary ray, they will be coming, they will be splitting into two types, and here also what you will get a double refraction. But if you see the in C case, the case number C, then what will happen? The crystal optic axis and the incident beam axis, they both are same, in the same direction. So since they both are in the same direction, even after split of E ray and O ray, that means extraordinary ray and the ordinary ray, you will not be able to get the double refraction here. Okay, so that means your crystal optic axis as well as your incident beam here, incident beam direction, they both should be same. They both should be different, so that the double refraction should take place. Okay, and that is the birefringence, and this birefringence is given as NE minus NO. That means the refractive index of this is extraordinary, this is the refractive index of ordinary. Okay, and there is another so the optical path length is given as NT here, and another terminology which we'll see in the next slide. I think that is retarded. Okay, we'll see. So this is about this elliptical polarized light. So linearly polarized light I have told you, and let's say the ordinary wave and the extraordinary wave, they cannot completely merge with each other, but if they are propagating through a same axis and mutually vibrating in the mutually perpendicular direction, then what they will do, they will add themselves by vector addition, and due to that, currently if you are seeing extraordinary wave is this, ordinary wave is this, so you will get a elliptically polarized light instead of getting so this is a circularly polarized light, but linearly polarized light, how it is generated I have told earlier. So now you are getting elliptically polarized light. Okay, And the optics of this polarizing microscope, you have to see to, 2-3 components here. One is compensator here and another one is polarizer here. So these are the two things which we keep for compensator and polarizer. And there is another term also called analyzer. Okay, so polarizer and analyzer, these are the things we keep for to view the material in a polarizing microscope. Okay, and these are the retarders. So what do the retarder do? And so retarder, they put a phase difference between your ordinary ray, that means O ray, and E ray. They put a phase difference, and that phase difference might be lambda, lambda by 4 and lambda by 2. Lambda is the full wave retarders, lambda by 4 is quarter wave retarders, and lambda by 2, these are known as the half wave retarders. Okay, and this amount of retardation they put, that is known as Ne minus No into T. Okay, so this is the formula for that. I think that concludes our chapter. So there are so in this session, I think not much time left. I'll take maybe 5 to 10 minutes more if that's okay with you. So now problem like numerical problems are there. There are 7 or 8 questions, just multi-Q questions, MCQ questions are there. So if you are able to see my screen, so we'll just go through that. So I think I have explained all the concept through in this lecture. So I'll read the question, then let me know whichever answer do you think is right. So first question is, what is the nature of the recessed ring in the phase contrast microscope? So one is opaque, transparent, semi-transparent, and either semi-transparent or opaque. Yeah, so can anyone tell me what is the answer to that? Hello, am I audible?
Yes, sir. Audible.
Okay, so yeah, what is the nature of the recessed ring? So here you can see the phase contrast microscope is written, right? So in the phase contrast microscope, the recessed ring is the phase plate. Okay, and this phase plate is an etched, it is made up of glass, okay, which is etched. It is at a particular thickness, and it has been made in such a way that the intensity will be, the amplitude will be reduced by 70 to 75%. Okay, that means some amplitude, some intensity we are letting we are letting them pass through this recessed ring, right? That means the correct answer will be, it should be semi-transparent. So the phase plate I have, if you remember, I will go just phase contrast here, this one, phase plate. Okay, this will be the semi-transparent. So this is called as the recessed ring, that is that. And the next question is, which of the following statement is correct for the opaque stop microscopy technique? So the opaque stop microscopy means, opaque stop means we are putting a stop. I have told you in the dark field microscopy that how we are putting, let's say this is our, and we are allowing only our incident beam like this, and this central portion which we are blocking our all the rays, so that is known as the opaque stop, and this microscopy is known as opaque stop microscopy. Okay, so in opaque stop microscopic technique, whichever statement is correct, the background of the image looks dark. So if we are not allowing our central portion of our light, that means we are blocking a large portion of our undeviated light. Okay, so the background will be dark. So this statement, the background of the statement is dark, that means this statement is correct. Then the statement 2, only the oblique beam is allowed to pass through. Yes, that is also true, because it will go and we will have some kind of reflection or diffraction technique which will be making sure that our oblique beam will be going to the incident to be incident on the sample, and then from there the diffracted rays are only, so these are the non-diffracted rays, and only the diffracted rays are calculated. So this one is also true. Only the central beam is allowed to pass through. If we are putting an opaque stop in the center, then the central beam will not be able to go through. That means this sentence is wrong. So out of the option, which one is correct? Only one. So this one is correct.
Only 1 and 2.
Yeah, only 1 and 2. Okay. Then the next thing is, which among the following is used to split polarized ray into ordinary and extraordinary ray? Which one? I think I have told you in this class. Can you answer? Any one of you? Polarized ray into ordinary and extraordinary. Remember, calcite is used for.
Calcite.
No, not calcite. Calcite is used for double refraction. Phase plate is used for. Phase plate is used for the retardation, and this thing glass is not used. So the answer is quartz. Okay. So calcite is used for double refraction, but quartz is the answer, which is the polarized ray into ordinary and extraordinary. Okay. Calcite is means there is a difference between polarized ray and so here if you see whether I have mentioned it or not, I think I have not mentioned it here. Yeah, here. So here quartz, calcite and rutile, these all are optically anisotropic, right? But here the out of those things only quartz allows the ordinary and extraordinary. It has the ability to split it. Okay. So like it is the difference between double refraction and I said birefringent. Okay, so same thing. So quartz and calcite, though calcite is using double refraction, but it is not able to split the polarized ray into ordinary and extraordinary. So the correct answer will be quartz. Okay. Yeah, so it is a birefringent. So it is calcite can do double refraction and birefringent can be done by quartz. And question 4. Okay, which is the following statement is correct for phase object? Yeah. So what this should be an easy one. What is the answer? Yes. The velocity of the emergent ray remains same. The energy of the beam is different. Change the amplitude of emergent ray. Shift the phase of emergent ray. Which one is correct? Hello.
Taking the number 1.
Which one?
C, sir.
B. I'm not
C.
Change the amplitude of the emergent ray. No, the phase object amplitude is changed by amplitude object. Okay, the phase object is the shift the phase of an emergent ray, right? Here, if you remember, just a minute. Here, okay. So amplitude object will reduce the amplitude. Phase object will retard the phase. That means it will decrease the phase. Right. So the phase object is what it will do. It will shift the phase of an emergent ray. Right. Here the phase object is mentioned. So D will be the correct answer. Velocity of the emergent ray not true. Energy of the beam is different not true. Shift the phase of the emergent ray is the correct answer. Similarly, which of the following statement is correct for the opaque stop microscopic? Okay, so we have already discussed the opaque stop microscopy. So also known as also known as the sensitive dark field microscopy. Yes, opaque stop microscopy is known as sensitive dark field microscopy. Why? Because we are allowing the diffracted beam to be captured. We are not allowing the undeviated beam to capture. The background of the image looks light. No. Stop the diffracted beam. The background, if we are allowing the diffracted beam, that means the background of the image cannot look light. This is wrong answer. This is correct answer. stops the diffracted beam by using a phase plate. No, in opaque stuff microscopy we are not using phase plate. Phase plate is only used in phase contrast microscopy. Okay, and then both A and B, this is wrong, so A is the correct answer for opaque stuff microscopy. Okay. Yeah, so here is the explanation. Opaque stuff microscopy is known as sensitive dark field. Background is dark and inclined surface. So this is the thing we use it for to seeing the inclined surface. Okay, why the inclined surface? Because let's say this is our incident beam, and the incident beam are falling like this and like this. So what is happening in the inclined surface? Inclined surface, the emergent ray will go like this, and if I put my objective here, all the emergent ray from the inclined surface I will catch, not this rays. Okay, they will all be going away. So that is why this methodology is used to see the inclined surface. Then comes this is a little bit tricky question. Two specimens having the same thickness, that means T will be same but different refractive index N1 and N2. Which of the statement is incorrect for phase contrast microscopy? Okay, both specimens have same contrast. Do you think both specimens have same contrast? They cannot be, because since the refractive index is different, so that means the NT will be giving to optical path length. Optical path length is directly, it is dependent on the optical path length is, it is related to the intensity, right? Because it is related to optical path length is related to the phase is related to amplitude related to the intensity is related to the contrast. Since they are both having different refractive index, so they cannot have same contrast. So this is wrong. Specimen 1 have higher contrast, so specimen 1 is having less low refractive N1, yeah. So specimen 1 is having lower refractive index than specimen 2. So optical path length of the so N is higher contrast. So optical path length is directly proportional to the contrast. So optical path length of, let's say, N1T will be less than N2T. That means the contrast of sample 2, so contrast of specimen 2 will be greater than contrast of specimen 1. So this is also not wrong. Specimen 2 have higher contrast. This is correct. So the correct answer is both A and B. Okay, you understood how I am connecting the optical path length to the contrast. Okay, so path length means it will eventually give to phase difference. Phase difference means it will eventually give to amplitude, and subsequently it will give to intensity. Intensity will give to contrast. So each time you have to do a calculation, you relate like this. Okay, from path, how I am coming to the contrast one. Okay, and yeah, so this is, I think I have told, in optical geometry for dark field microscopy, the numerical aperture of the objective is this, the numerical aperture of the dark field condenser. So this should be then an easy one. Can any one of you answer? Okay, so in optical geometry I have mentioned while explaining the mechanism of dark field microscopy, I have given one paragraph, and in that paragraph I have given two important points, like how the experimental parameters you should see, that we will be able to see in dark field mode. So in that thing, if you see the first point, I have it is mentioned that the numerical aperture of the objective should be lower than the condenser and dark field annulus. So that the numerical aperture of the objective means the objective which captures the diffracted ray after the interaction of the incident beam with the specimen. So it should be low, so that less amount of diffracted ray should be captured and should be sent to the objective for the viewing. Okay, so that is why the numerical aperture of the objective should be lower than the numerical aperture of the condenser. And yeah, filters are used to adjust the It's an easy one. Filters are used to adjust the intensity of the illumination as well as wavelength of the illumination. So that means this is the correct answer. It's not used to used to amplitude of the illumination. So this is the correct answer. Okay, and yeah, I think this is the last question. So the action of the phase plate in phase contrast microscopy is to make what? So the action of phase plate will be if you remember, a ring like structure was there, and this will be there. Okay, so the ring like structure was there, so this is 2, and through this the S wave, that means the surrounding waves are going through this, the D waves are going, the diffracted waves. So the S waves are plus lambda by 4, their phase are accelerated by lambda by 4, and the D phase are retarded by minus lambda by 4. So S wave both S and D wave advance by, no, this is not correct. S wave advance by point lambda by 4, D wave, yes, this is correct. S wave retarded, this is not correct, this is not correct. So B will be the answer. Okay, so yeah, these are the problems. I think these are the problems. Yes, so these are the problems. Some of the so this, I think this week assignments are also based on some of the concept, not based on any numerical problem. So if you have gone through all these questions and all the concepts, then you can solve them and try to submit them from the before the deadline. Okay, yeah, so okay, if you have any doubts or anything, then you can ask me, mm, or else we can close the meeting. Thank you all for attending. I will upload the documents, the presentation documents, as well as the recording in the folder, and I think the team will be sharing them with you, so you can go through them again and check. If you have any doubts or anything, you can mail me, or we can discuss this in the next lecture as well.
Thank you.
Yeah, thank you. Have a happy weekend.
Same to you.